Hello everyone, let us start lecture 13. And topic explanation corrosion event on the basis of mixed potential theory. And we have started our discussion on this particular situation, area effect on the corrosion of active component when connected to a noble component. So, there we started with this particular diagram, and we have realized that we cannot explain this corrosion event if we consider current density. Instead of that, we have to take current. So, once we take current, so then this unit becomes A, and this I0 point would change. Now, here we are talking about everything in terms of capital I. So, now if it is 1 centimeter square, this is all the time 1 centimeter square, this does not change. So, this is also 1 centimeter square. So, in case of 1 centimeter square, I0, capital I0, that means current is equal to current density magnitude wise. So, their units are different, but magnitude wise they are same. For example, here we have given an example. So, if I0 over small I0 is 10 to the minus 5 ampere per centimeter square over platinum of that hydrogen evolution reaction, the capital I0 of the hydrogen evolution reaction on platinum with the same area would be same, but the unit is one case ampere per centimeter square, another case it is ampere. Now, I can term these values, I can write this particular thing as capital I0 instead of small I0, and that unit becomes ampere. Now, when we consider 100 centimeter square platinum connected to 1 centimeter square zinc, so the capital I0 over that 100 centimeter square area will shift to the right. So, let me plot everything in blue color. Okay. So, that point will come here. After multiplying area with that exchange current density of hydrogen evolution over platinum surface. Now, it will also follow the same slope beta. So, will so this is the individual, that means the IC variation, this is IC hydrogen, oh sorry, I should mention capital I, IC hydrogen over platinum surface. Now, we have to add this current density also as per the mixed potential theory with this blue dotted line. So, if we add that, so this addition will be this line. So, this is and this would extend definitely. So, this line is nothing but I or IC total equal to IC hydrogen over platinum, or I should mention this. So, this is I total C equal to IC hydrogen over platinum of 100 centimeter square plus IC hydrogen over zinc. So, I can remove this terms of 1 centimeter square. Fine. I should mention side by IC hydrogen, and remember these are all capital I on zinc surface of 1 centimeter square. Fine. And this particular line also would be I0 only, because this area is not changing, it is always remaining 1 centimeter square. Now, where would it meet the criteria of mixed potential theory, where I could see that the charge balance is maintained. So, I could see that the charge balance is maintained at this particular point. So, what will be this situation at this point? I could see that equal to, or I equal to I A of zinc. So, this is the condition, and then what will be the mixed potential? So, the mixed potential is this is the mixed potential. So, E mix when this condition is meeting, when zinc 1 centimeter square is connected to platinum 100 centimeter square. Now, if capital IA is the new dissolution current of zinc, remember we are saying current, not current density, and we know that the current density, we know that the current is not proportional to corrosion rate, rather current density is proportional to corrosion rate, since W area is A, T equal to I A N F capital A. So, where I is current in ampere, E is atomic weight in gram, and N is equal to number of electrons, F is 1 Faraday, which is 96500 coulomb, and A is equal to area. So, now we could see that if we consider the corrosion rate to be this, then this quantity is not proportional to corrosion rate, because this can vary. but if we consider this quantity, that means I by A, that is proportional to the corrosion rate. So, we have seen that before. So, now if I A is equal to I C hydrogen over platinum of 100 centimeter square plus I C of hydrogen over zinc of 1 centimeter square, then I need to find out I A from this. How do we find out? Now, if I get to this same plot here, now since it is in log scale, now this particular line is farther left to this line. So, the effect of that addition of this particular current for this particular current related to the hydrogen evolution over zinc surface on the total IC would be very minimum. We will see that later. So, actually we can consider it to be IC hydrogen over platinum 100 centimeter square. So, IA would be IC hydrogen over platinum 100 centimeter square divided by 1 centimeter square, because whatever this current requirement current is flowing between 1 centimeter square zinc and so this is situation is like this is 1 centimeter square and this is 100 centimeter square, this is 1 centimeter square. So, the current flow between these two, so the same current is flowing over this smaller section. So, this is anode and this is cathode, and here it is platinum and here it is zinc. So, the same current is flowing. So, if the same current is flowing, the current remains same, but when we are considering converting into current density, we are seeing that we have to divide it by the area of the anode. So, area of the anode remains 1 centimeter square. So, now you could see that the corrosion rate, which is nothing but the I core when zinc is connected to platinum over 100 centimeter square area, okay, which is almost is much higher than the corrosion rate of zinc when it is connected to 1 centimeter square area of platinum. So, this is the crux of the problem what we experience in case of copper plate and iron rivet. So, this is the problem what we experience. The iron rivet dissolves quicker than the situation where area of copper and iron are same. So, here cathodic area is much higher. So, this is cathodic area and this is anodic area. Since we have a big two plates, so we have rivets, small rivets. This is iron rivet or steel rivet, and this is copper. So, we could see that the current density related to the dissolution of iron over iron becomes much higher than the situation which is proven here, than the situation where the iron area and copper area both are same. This is, if these are same, this is iron, this is copper. If they are same, the situation would be much less aggressive. This is proven here. For example, when 1 centimeter square area of zinc is connected to 1 centimeter square area of platinum, the corrosion rate was here. Now, once the platinum area is increased, the corrosion current has become here, and the corrosion current density would also increase in relation to the area increment of that noble component. And remember, here, as we have mentioned before, the noble component or the cathodic component is decided by the reaction, that means the cathodic reaction is taking place on that cathodic component. Here also the cathodic reaction is hydrogen evolution reaction, and that is taking place over the platinum surface, and that is why platinum becomes cathode and zinc becomes anode. And in case of copper plate and iron plate, iron acts as anode and copper acts as cathode in sea water, and that time cathodic reaction is O2 plus H2O plus 4E equal to 4OH minus, and anodic reaction, this is cathodic and this is going to be anodic reaction. So, now this is the situation what we experience when we have active component having less area and noble component has higher area in a galvanic couple, and that is practically a very dangerous structure design. So, we while designing structure on the basis of if we see that there is a chance of aggressive corrosion, we should not keep any structure where cathodic area is higher than the anodic area. So, our interest should be always the cathodic area should be less than the anodic area, or rather if we can protect the cathode surface and leaving the anode surface exposed, that would be great. For example, if we recall in the lecture in the corrosion part 1, we discussed that in a tank, if we have gladded stainless steel at the bottom and the leaving some iron part on the top of the tank, so then it is always better to coat the bottom surface, that is the stainless steel, so that the cathodic area is reduced. So, the design criteria is the cathodic area should be less than the anodic area, and so that the area influence on the increase of the anodic dissolution rate should not be felt. We have seen that if we increase the area of cathodic region in a galvanic couple between an active metal and noble metal, then the corrosion rate increases, and the explanation for that, we cannot explain it from the plot of potential versus log of current density, rather we have to explain it from the plot of potential versus log of current. So, the unit in the x axis changes from ampere per centimeter square to ampere, then only we will be able to appreciate the effect of increase in area of the noble part in that galvanic couple. Now, we also need to see that what would happen if we increase the anodic area keeping the cathodic area fixed. So, in order to understand that, we have to also make use of potential versus log of current plot. So, if we try to see the situation, if we try to see the anodic area increases, cathodic area remains fixed. So, how to explain that situation in that galvanic couple? So, we have to plot log I. Now, it is interesting to note that we are using capital I. So, that means the unit becomes ampere and this becomes potential, which is in volt. Now, we have already mentioned that we will be talking in terms of standard hydrogen electrode. So, now if we try to see the hydrogen evolution reaction, that means if that couple, that cathodic and anodic area, considering this situation, if we dip that particular couple in an acid, where if we consider that hydrogen evolution reaction is my cathodic reaction. So, that would happen on both anodic and cathodic surface. So, now this is E equilibrium of, let us say we are considering zinc, and then this potential is decided by the pH of the solution. So, when we consider mixed potential theory, so this point is I 0 zinc of zinc, and this point is I 0 hydrogen over zinc. Now, if we consider there to be 1 centimeter square, so here we are considering 1 centimeter square. So, this is with reference to 1 centimeter square, and this becomes my E core of zinc. Now, if we try to change that current density into current, if area remains 1 centimeter square, so then that would also be I 0, because this in multiplied by 1 centimeter square becomes my current corresponding to exchange current density. So, now this is also becoming, this would also become I 0 hydrogen over zinc, because we are considering 1 centimeter square. Now, when we couple platinum of 1 centimeter square, this value will not change, because that is decided by the pH, but we will have I 0 hydrogen over platinum surface of 1 centimeter square area. And then as per the mixed potential theory, the way we have done previously, so we will do, and then we have to add it, because we have to consider the mixed potential. So, we continue this, this becomes my E mix when we are connecting zinc and platinum of 1 centimeter square each, and I 0 of hydrogen over platinum surface is very high, and this is nothing but I C total, which is I C hydrogen over platinum surface plus Ic hydrogen over zinc surface, and this particular current density is IA total equal to IA zinc because here only one anodic reaction is taking place, and so these two are Ic total equal to IA total. We are expressing in the form of Ic equal to Ia. Now, last time we have increased platinum area and then without changing the zinc area. Now, if we change the zinc area, so let us say zinc area has been changed to some arbitrary 10 centimeter square. Okay. So, now 10 centimeter square if we do it, so I0 would become then I0 into 10. So, then this point will come here. Similarly, this also have equal change I0 hydrogen over zinc surface equal to I0 hydrogen into 10. So, now we can draw that line like this. So, this becomes my E chord, and interestingly we will see later on with the calculation that this point does not change even if we increase the area, because the slope, if the slope remains same. So, this point will move right side, only thing that change will happen, but remember again this change, this becomes my Ia equal to I chord, but it will be also equivalent to I chord when 1 centimeter square area, because nothing we are changing, only changing because both the I0s will change in a multiplied manner. Now, when we talk about platinum now, so this point will not change, this would remain as I0 hydrogen over platinum 1 centimeter square, this point will not change, but now we have to add this line and this line. So, if we add them, that comes, let us say it comes here, because since this point is shifted to this point after considering capital I. So, now it will also shift little bit. So, it will come like this. Okay. Now, we have to continue this particular plot. Okay. So, it will come and meet this point. So, this line is nothing but I total C equal to Ic hydrogen over zinc of 10 centimeter square area plus Ic hydrogen over platinum 1 centimeter square area, and the new E mix is this point. So, this is E mix new. So, my corrosion rate has come to, we do not know the corrosion rate, rather we know the current. So, if we try to see what is the current corresponding to dissolution, so this is nothing but Ia of zinc of 10 centimeter square area. So, now in order to find out corrosion rate because of the increase in anodic area, this would become Ia zinc by 10 centimeter square equal to I cor nu when zinc is 10 centimeter square. When zinc is 10 centimeter square. So, that will be change in the overall diagram, but by looking at this, apparently it looks like the corrosion rate of zinc should increase, but if we do some numerical analysis, we will see interestingly the corrosion rate of zinc does not increase, rather it is lower than the corrosion rate of zinc when the equal area of zinc and platinum are connected. We will see with an example, and remember one condition is to be met, that every time when we are talking about this potential log current or current density plot, we are assuming that uniform dissolution is taking place and uniform reaction of cathodic and anodic reactions over cathodic and anodic surfaces are taking place. This uniformity is one of the major criteria for drawing this particular diagram. Then only we will see that yes, increase in anodic area rather decreases the overall corrosion rate of zinc compared to the situation where equal area of anode and cathode are connected. And in other situation where cathodic area increases as compared to the anodic area, corrosion rate of anodic region will increases to a great extent. So, let us stop here. We will continue our discussion in our next lecture. Thank you very much.